Alright, so in this video we're going to discuss what an antiderivative is. And it is pretty much what you would expect. It's the opposite of a derivative in the sense that anti usually means. But before we really dive into that, I want you to answer the very first question. What could f of x be if f prime of x, or the derivative of the function, is 8x? So we're going to start working backwards and answering questions of this nature. So I want you to just give this first one a try and see what you come up with. Alright, so you should have circled more than one answer here. That's going to be the fun part of this. So if we go through one at a time, the first one, 8x squared, well, that can't have this as a derivative because if I were to actually derive this, right, it would become 16x, which is not 8x. All right, for b, if we derive that, we're going to get 8x. Oh, good. Yeah, that works. Okay, for 2x to the fourth, I'm going to get an 8 here, but that's going to become an x cubed, so that won't work. An 8, well, the derivative of that's just going to be 0. Here we have more than one piece, so this would become 8x, but then the second piece would become a plus 6, so that's out. For f, okay, we'll get the 8x, and the plus 6 goes to 0, so that is 8x. Okay, for the next one, again, we're going to get the 8x here, and another constant derivative is just going to go to 0 again. And for the last one, we have that 4x squared piece that has consistently shown up, and then another constant. So remember, pi is a constant. So all four of these actually represent the antiderivative of 8x, or essentially the function that if we took the derivative of it, it would result in 8x. So this is kind of what makes integration a little more challenging than finding derivatives. When we find derivatives, there's a single answer. It's not ambiguous in any way. But when we take the antiderivative, there's kind of a problem, right? We could have had any of these functions. So if you stop and look at what they all have in common, well, they all have a 4x squared. That is not up for debate. But where they may vary is in some sort of constant being added at the end, right? Essentially, this one's a plus 0. So they can have any sort of constant added on, and since the derivative of a constant is simply 0, it doesn't affect their derivative. So for all antiderivatives going forward, you're going to add some arbitrary constant c. I know, still, it is exciting, finally getting to integration. So essentially, the true antiderivative of 8x, if we antiderive f prime of x here, would be 4x squared plus c, where c is any constant we can possibly imagine. Positive, negative, big, small, even pi. It doesn't have to be rational or anything. So anything of this form is considered the antiderivative of this function. Okay, so hopefully that will help this joke make a little more sense to you. It's hilarious, I know. We're going to do some quick vocabulary. So a function f of x, and notice that we are now using a capital F here, is the antiderivative of a function f of x, the way we normally write it, or the lowercase f, if f prime of x equals f of x. So essentially, we know something's the antiderivative of a function if we're able to take the derivative of it and end up with that other function. For all x in the domain of f, the process of finding the antiderivative is antidifferentiation. So there's a couple words in here I want you to make a note of. I'm coming. The antiderivative of a function is like the noun, And the process of finding the antiderivative is referred to as antidifferentiation. Okay, so on to the second set of vocabulary. We're going to say the family of all antiderivatives, since the plus c kind of creates this whole family. Of a function f of x is the indefinite integral, which we're going to kind of revisit what that even is. The indefinite integral, so not the finite integral that we looked at today or yesterday, but the indefinite integral of f with respect to x and is denoted by the integral sign without an a or b bounding it, f of x dx. And then we're going to kind of go more in detail with that on the next page. Okay, so the family of all antiderivatives of a function is represented by the indefinite integral of f with respect to x. Okay, so on the back of your notes there's like a better diagram of this. Again, the integral sign we've already spent some time with. We call what it is we're taking the integral of the integrand. This is the variable of integration, or what we're integrating with respect to. And then the output of this, in terms of the antiderivative, is the indefinite integral, and then plus that constant of integration. Okay? Alright, so let's also jump into some notation things you should get used to. So there's two ways integrals and functions can be represented. So one way is kind of like what we were doing on the previous page, where I give you a derivative function and you integrate it to get the regular function without the derivative notation. So that's probably the first way a lot of people see it. So you start with f prime of x, you integrate it, integrate f prime of x dx, and the output is f of x without any derivative notation. Okay? So basically, you're kind of going in this order here. So if you integrate a derivative function, you get back the original function. The other way this might be notated is we simply have a function. It's not written as a derivative, and then we actually integrate it. And when this happens, and you may have noticed this briefly in the definitions we just looked at, it creates a capital F of x. Kind of like this new function we don't yet have anything for. So those are the two things you'll see, f prime going back to f, or f going to a capital F, to notate that that's like the next degree or power above the current level you're at. The other thing I want to talk about is how it pertains to our physics, right? So back when we first started doing this, we talked about how when we take derivatives, we start with the position function, which a lot of times we'll use s of t, or maybe even x of t is a common way we've written it. And when we derive the position, we get the velocity. And when we derive velocity, we get, what color do we want to use? Oh, this will be exciting, brown. We get acceleration. Okay? So again, we go from position to velocity, or how the position is changing, and then from velocity to acceleration, or how the acceleration is changing. So now that we're anti-deriving, it works in the opposite direction, right? So if you start with acceleration and you anti-derive it, you're going to go back to velocity. And if you anti-derive velocity, it's going to take you back to position. So yes, expect these questions to become very regular again.